if there are no questions, although I'm happy to take questions now before we move on. Okay, so we move on to, we talked a lot about structure. Now we're going to move on to talking about the chemistry within these materials. I'm trying to understand the chemistry by probing the chemical components themselves, right? Each of the species within the speciation within the material. So in terms of the useful resources, I have found that these books and this book and software have been extremely helpful. This is a fun read if you ever want to read the derivation of X-ray absorption spectroscopy and also the derivation of the extended X-ray absorption fine structure or EXAFS equation at different levels. This is a fabulous resource written by Scott Calvin. And one of the reasons why you see the different characters is they each represent different personalities in the lab. So if you are someone who theorizes and plans before they go into the lab to carry out the experiment, there's a track, there's an animal for you. If you're one of those, if your personality is more, let's just get into the lab and break some things and then I'll learn from it, there is an animal that fits that personality as well. So depending which personality suits you, you can follow the different tracks for trying to understand the derivation of X-ray absorption fine structure, which is why the book is called EXAFS for Everyone. Okay. So, so that's that. In terms of software, for many years now, Bruce Ravel has of NSLS, the NIST beamline at NSLS at Brookhaven have provided the community with a software that is extremely useful for data processing. It used to be that you really had to do inline processing at the terminal, which is fine. But there's now also, for many years now, there's a helpful GUI where you can process your data in Athena and then fit it in Artemis, and also prep your samples with this periodic table that you see here. That's called Thesis, and the whole package is called Demeter. So if you ever use, if you ever need to process data, this is a very useful package, although it's not the only package out there. I highly recommend it. Although it's the front end to FEF, which is really the software that processes all the X-ray absorption and interaction for the graphical user interface. Okay. Okay. So we continue the discussion of local structure, but now trying to probe the local structure with X-ray absorption spectroscopy. Not only do we have an understanding of local structure from XAS, but we'll also have information of the oxidation state with chemical specificity. So if you are interested in, you know, the nickel as it differentiates from manganese, it differentiates from the cobalt species in NMC, you can probe all of that you might not be able to from X-ray diffraction or even PDF, given that they all these 3D transition elements have similar X-ray electron densities. Okay. So in terms of how X-rays interact with core electrons, if you have an incoming X-ray at a certain wavelength, you can have ejection of the core electron that's shown here. And if this atom is in space, absence of nearest neighbors, then the absorption as a function of energy, so you can sweep through all the energy, absorption energies that's required to excite core level electrons, like from 1s, 2s, 2p, 3s, that sort of thing. Then the signal would look something like this, where you just have the absorption edge and then decay of signal as a function of energy away from the absorption edge. Realistically, real physical materials, right? You have your atom of interest, and then the electron orbitals around the neighboring atom, a particular r distance away, will cause these fine structure undulations that you see here. So the signal will change as a function of what type of neighbors you have, and also where these neighbors are in terms of, you know, real space distances away. So what we really want to understand from all of the signal in terms of the X-ray interaction with that of with that of all these core electrons is we want to understand, well, how does, well, one, what type of neighbors you have, and also what where the neighbors are affect the signal. Okay, and just by looking at the near edge region right here, we can get a lot of information already before we do any Fourier transform, any anything, and modeling. We can understand a lot already. Okay, so in terms of the likelihood of generating the signal, the absorption probability, right? If you're below the absorption energy, the absorption probability is pretty low. You need at least that amount of energy to ionize, so like eject the electrons out from the core level, right? Not, the probability is low, but not impossible, right? So we map that. If there's an X-ray coming in, it ejects an electron from the core energy level, and it becomes a photoelectron, right? In the continuum, we can map that, and we plot it as a function, the absorption probability as a function of energy. So you have to rotate your head by 90 degrees. Okay. So what are all these, once, you know, there's ejection, the photoelectron interacts with the neighbors. So we have the single scatter event. So it, you know, goes, scatters, comes back, say. So this is a linear relationship. If there are multiple scattering, you know, it could have interactions with the nearest neighbor, and then this nearest neighbor interacts with the next nearest neighbor, and then you could have more complicated multiple scattering events that are represented here. And it could be that they, you know, they go back. These photoelectrons interact with each other in a number of complex ways. Okay, so when we're talking about XANES, we really are going to deal with the simplest case, which is the single scatterers here. But there are multiple scattering events, particularly in the post-edge region that's really close to this absorption energy here. Okay. So at the core, when you have an ejection, if there's enough energy from the X-ray, once you sweep your energy levels, if there's enough energy to eject the core level electron, particularly, let's say from 1s, that's why it's called K, then you're going to see that you're going to be able to measure that photoelectron. Okay. Now, you generate, well, if the electron is ejected, now you leave behind a hole. And from here, you know, you can get more complex processes like fluorescence, where an excited, a higher energy electron will then relax to where the hole was, and then that will generate a different energy, this K alpha, or if it's from the M level, you know, it could be this K beta. So there are multiple processes that will then ensue once you eject this core level electron. Okay, and then there's also Auger processes, and that gets, you know, even more scattering events. But for the purpose of XANES, we can get to Auger when we talk about XPS, but for the purpose of XANES, we're really interested in this core level type of excitation. Okay. And in terms of the nomenclature, you know, how to name all these processes, you know, that's pretty well established. And we'll focus mostly on the K level type of the K edge. So that's excitation from the 1s energy level. Okay. Now, the XANES energy region, what we're really interested in is, okay, where is the absorption? So what is the energy that's required for the 1s electron ejection? But before that, there's often typically information from what's called the pre-edge peak. And then there's also information in the post-edge region. So within about 50 EV of the absorption edge, that's right here. That typically tells you, gives you information about the multiple scattering features that are going on in the material. And then at even higher energies, we can have information about the fine structure. So before you transform this normalized spectrum, we can get information about the fine structure itself. Okay, but since this is spectroscopy, we are confined to the physical rules of chemistry and physics, which is if you are ejecting an electron from 1s region, which is a Garrod orbital, the excited level, the electron transition has to satisfy the orbital angular momentum selection rule, which is that delta L has to be plus or minus 1. All right, so for those of you that have taken chemistry, this might ring a bell when it comes to spectroscopy. So if you're going from 1s, then you have to go to a p orbital. You have to go to a p state, right? But often, if you're dealing with a 3D transition metal, so here this is for vanadium, if you're dealing with 3D transition metals, there are unfilled, the orbital is unfilled, right? For vanadium, that's 3d3. So there's an unfilled orbital in the d orbital. So the electrons can also go there, but that's forbidden, right? So the probability would be very low for that. But we still see pre-edge peak. So what does that really mean? So that's what I'm going to walk through in terms of the theory and trying to understand how does this small pre-edge peak give us so much information when it comes to oxidation state and also the coordination environment. Okay, so in terms of trying to understand and gathering information from the pre-edge region, we can get out information such as oxidation state, coordination, also bonding characteristics. The absorption edge is the ionization, right? The ejection of the core level electron that gives us information about the oxidation state. And then the post-edge region will give us more information about the interatomic distances and bonding geometry. But I should say it gives us information based on standards because it is incredibly difficult to fit the near edge region. We can fit EXAFS, but in terms of fitting the post-edge region here within XANES, which is 50 EV of the absorption line, it's really difficult because we have to take into account the multiple scattering processes, and that's not so easy when it comes to, that's not trivial when it comes to using software like DFT, right? It's computationally expensive, and how do you know when how do you encompass all of the multiple scattering processes? So we can use measured standards to try to understand, what kind of structure we really have. Okay. So in terms of operations of X-ray absorption, near edge structure, spectroscopy, it is essentially what you think it is, right? You have an incoming X-ray beam here that you've made monochromatic because you have filters and crystals in place from the synchrotron source. You have it coming in, and you could do one of two experiments. You can measure fluorescence that comes out. So if you have low concentrations, you could do fluorescence. You could also do transmission and measure the transmitted beam here. And so the relationship between that is very similar to Beer's law, right? Is that your transmitted beam is the original beam, the incident beam, I naught, times the exponential decay based on the absorption coefficient, and that changes as a function of energy that you're at, times the thickness. So T is thickness of your sample. What's also really interesting about this technique is fluorescence is extremely sensitive. And in fact, you can detect your own signal. So when this signal comes out that you see here, sometimes it will also come back and you can detect the signal again, which is pretty interesting. And in fact, many years ago, there was an earthquake out in Virginia, or maybe it was West Virginia, or maybe both. But anyway, there was an earthquake back in 2014, maybe 15, and we could detect that because there was vibration in the detector, and we could like record the fluorescent signal because it was vibrating the detector so much that we could actually detect it. So anyway, fun fact about detecting earthquakes. All right, so why does this matter? You know, why do we need to know linear absorption coefficient? Well, that now ties back in with something that you are probably all familiar with, which is X-ray diffraction. So here we see if we have X-ray absorption, so this is the mass absorption coefficient, which is normalized by, so it's mu divided by the density of the material. So here's an example of lead. So we can map out all the excitations, right? The K edge, the 1s ejection, 2p, the L1, L2, L3 edges, and so on and so forth. And we can even go further, right? So that's a mass absorption coefficient as a function of wavelength. Okay. So we can see all of that. Now, this is for lead. We can do the same for copper. And one of the reasons why I bring up copper is because we often use copper K alpha as a X-ray diffraction source in the lab. And one of the reasons why this is of interest is we can map out the same. So this here on the bottom is the X-ray energy in KeV, but that's just related to the wavelength. If you flip it, it's just HC over lambda. So if the wavelength divide HC over that Planck's constant times the speed of light gives you energy. So essentially it's the same information, but now different representation. And so what you see is you have the K edge. You could also have here for copper, the K alpha and the K beta edge. Now, one of the reasons why I use nickel is because a nickel filter, I should say, is so you isolate the K alpha edge because nickel has an absorption energy that is right in between the K alpha and the K beta for copper. Right. So when you want to rule out the K beta edge, put in a nickel filter so that nickel absorbs all of the energy that's coming in. Right. So there's fun fact relationship between X-ray absorption and X-ray diffraction there. Right. So you can utilize the material property to set up your X-ray diffractometer so that you get just signal from the copper K alpha instead of copper K beta as well. Okay. So that's an aside, but that's fun to know, or useful to know. Okay, so in terms of then tuning chemical specificity, if you have elements within your material that you want to isolate, what you would want to do is pick the energy, right? So if you have something like NMC, you have lithium, nickel, manganese, cobalt, and oxygen. Typically, you can't probe all of those species at the same beam line because the K edges for the transition metals, those energy levels are much higher than that of your lithium and that of your oxygen. So you can see here that the oxygen would be probed at a soft X-ray beam line, but the nickel, manganese, cobalt would be probed at a hard X-ray beam line. Now, that's the K edge. You could also go to L edge and go to lower energy, and you could do all that. So you can map out all the energies of every element, and then you need to then go and design, you know, which beam line you're going to send your proposal to. So here's an example for sulfur edge energies, going from K to L1, L2, L3, M edge. So that's from top to bottom, highest energy to lowest energy. So you could see here that, you know, for the 3D transition metals that we're interested in, typically the battery materials for lithium ions that we've discussed, right, contains vanadium, contains titanium, contains chromium, well, not chromium yet, manganese, iron, cobalt, nickel, all the 3D transition metals. You see that you have to get to a high enough energy, at least 4 4,966 EV, right? And so to go to a beamline that has both 2,472 and also about 5,000 EV is a really huge range for the monochromating crystal to achieve. So typically you have to go to 2 beamlines for that region. But the sulfur species is beautiful. So if you work on lithium sulfur batteries, XANES is, is a particularly useful technique because depending on the speciation, right, ranging all the way from -2 to +6, you can see that sulfur has a huge range of oxidation states that you can probe with X-ray absorption spectroscopy. Okay, so that's what you see here. So you can also do these beautiful type measurements and probe all the way from 0 valent sulfur. So that's the X-ray absorption signal there for the K edge. And you could see that the absorption edge shifts and increases as a function of oxidation state for all of these types of sulfur species. So you could see the power in just looking at the XANES signal, the near edge signal. You already have information about the oxidation state. So here you have higher oxidation state than that of S8. And you could see that the range is 9 EV, right? So you can resolve this energy change and understand the different oxidation states. You can also look at 3D transition metals. So here I'm going to focus on vanadium K edge because this is a really useful and extremely detailed, heroic paper. You can see the number of pages that are there, how detailed this paper is. So I'm going to focus on the vanadium oxides because there are lithium-ion batteries, materials of interest that are vanadate based. So I'll stick to that, but there's this paper, I would highly suggest you read it, from end to end, because it's extremely informative, even though it was done, 3 decades ago, more than that actually. So here you see an example of the X-ray absorption signal for the vanadium K edge, right? So this is pretty typical. What you have to do then is normalize the signal to something that you're more used to seeing, which is something on the right here. And so you have to transform the signal and subtract out this background here, sorry, this decaying feature. You basically set a background polynomial and then transform the information so that it looks something like this, where there's no absorption, and then you hit the edge, the absorption edge, and that's where the energy takes off. Okay. Sorry, the absorption probability takes off. Now, historically, this has been called a white line, even though clearly it's a black line on white paper, but it's called a white line because of the film that was used back in the day, that the signal would show up as white on black film. Okay, so it has historic reasons as to why it's called a white line. But I just call it the absorption edge. But if you see in the literature, the white line energy, it is the same, it's different semantics, but same idea. Okay, so what you can do from all this signal is you can quantitatively define what exactly is your absorption energy. So you just take the first derivative and you see the inflection point will be now set at, whatever energy you're at here. This is 0 beyond the absorption energy. So if it's vanadium, the expected vanadium absorption energy from the K edge, which is excitation from the 1s core level, at 5,465.1. And how you do that is you calibrate to a metal foil. If you don't have a metal foil, because you're working with a material that is, it's not stable for whatever reason, not really the problem here for battery type materials, but if you're working in geology or what have you, you can run into elements that are not stable, or you don't have a metal foil form, then you have to run your own calibrations that way, with different powders and stuff. But anyway, right, so that you would set this energy as the 0 energy, and that's what you see here. So now that's set as the absorption energy is now 0. So anything before that will be the pre-edge. Anything after that, higher energies will be the post-edge region. Okay. So you see here the probability. This is the absorption energy set as 0. So before that, for vanadium, for just vanadium metal, there is basically no pre-edge, but just the absorption energy here, and then all these multiple scattering type signals that you can observe. So what's really wonderful about this particular study is that you can track the oxidation state as a function of the absorption energy that's shifting, that's increasing, and you can also track the local coordination. So if you look, and I'll walk you through this, if you look very carefully at vanadium metal, which is 0 valent, to then vanadium oxide, VO, they're all vanadium oxide. Okay, so I'm going to actually spell out the stoichiometry. If you see VO, that's an oxidation state of +2. So what you notice here, all these peaks, these tick marks are all 0. Okay, you start to see the emergence of this shoulder, this pre-edge, right before the absorption energy here. So this is the octahedra that are within VO. Okay. So the pre-edge, though, is saying that there's an emergence of some absorption coefficient. So there's the absorption probability is increasing as you're increasing the oxidation state. Okay, because it's allowing the 3D, 4D, the 3D, 4P mixing that was forbidden before. So your absorption energy is 1s, exciting 1s to 4p, right? Because the electron configuration of vanadium is 3D. So the unfilled states are going to be in the 4p, right? The orbital beyond 3D. So that's your absorption line. But before you get there, the more you distort this octahedron, the octahedra here, and the more you distort the higher oxidation state, you see the emergence of this shoulder that becomes more prominent when you increase oxidation state to +3. And then when you have mixed valence +3, +4, so you're still increasing the oxidation state, you see this pre-edge grow. And then if you then increase to a +4 oxidation state and a +5 oxidation state, you see the pre-edge peak really grow. Okay, so I'm going to put all those spectra together so that you see them all in one slide. So let's look at the absorption edge here at 0. Absorption edge increases more. So the shift now, the absorption edge is like almost 20 EV above where it used to be. It used to be 0 for metal. Now at +5, the highest oxidation state you can have for vanadium is about 20 EV above where it used to be. And that's how you calibrate. You have to calibrate towards the metal. And the pre-edge regions grow as well. Okay. So already just by looking at the XANES without fitting the X-ray absorption fine structure, right, you can already tell that they're, you know, what kind of oxidation states you have. This is very useful if you're trying to understand how lithiation or sodiation or, you know, whatever intercalant you want to study, you know, how these species affect the local structure. And you could do these type of X-ray absorption experiments to tell you that. Okay. So that's pretty powerful. This is probably one of the most beautiful papers on X-ray absorption, despite the plots looking like they are from 1984. Okay. And so I'll wrap up here and we'll pick up here next time, but you can map out these beautiful trends in both the absorption edge as a function of oxidation state, the centroid, so where the 1s, 4p peaks are, you can map that as a function of oxidation state, the 1s 3D pre-edge peak, all of that. There are beautiful linear relationships that you can map out as a function of oxidation state. And you could do the same for the intensity, which is if you take the peak height and multiply that by the full width half maximum of these peaks for different ligands. So not only oxygen, but also, you know, all these other species like sulfates and what have you. and different local geometries like square pyramids and distorted octahedra and all of that, you can map out all these relationships as a function of, this R bar, which is the nearest neighbor ligand distances, what's called the molecular cage, right? This average distance to the nearest neighbor amongst all these different families of compounds. You can map out all these fantastically beautiful linear relationships to try to understand how the local environment is changing and also how the oxidation state is changing. Okay. All right. With that, we'll pick up here next time before we move on to X-ray solar electron spectroscopy. Questions? Yeah. Well, I will tell you that if that is really the answer.
But the one has to be transition.
Yeah. Yes, because so what is the angular momentum number for S? Okay. Yeah. Well, the delta L, okay, regardless, even if you didn't remember, okay, that's not the point here. That's not whatever the point, that's not the point. The point is the selection rule is that you can only have that transition when delta L, the chain of angular momentum, is 1 or plus or minus 1. So you can go up and down, but it's plus or minus 1. So you're probably thinking of the principal quantum number, which is 1. Oh, but it doesn't matter. So going from S to P is 1. P to D is 1. So you can go from P to D, right? D to S. You can't go from S to D. So that's delta L of 2. But my point is, so that's for the absorption. It's the high energy absorption, the high energy line. But my point is, you see that transition, you see the forbidden transition in the pre-HP because you are seeing basically the 1s to 3d transition, and that's only allowable. The probability of observing that absorption is allowable because it's actually mixing the 3d orbitals, mixing with the 4d. So it's just hybridization. That's allowing that to happen.
And not hybridization. As you're oxidizing.
Yes, because you're now also overlapping with the 2p of the oxygen. So, okay. Okay. Let me see if I have a slide which we'll go over, but we're not going to preview the next. Here we go. Do I have that? Okay. I thought I had that on this slide for looking at manganese, but all right. Thought okay. Maybe in my head I had like drawn that figure and I never did. But basically, yeah, you are increasing this pre-edge peak is increasing in intensity because you have distortions to the octahedral geometry. So it goes from this VO, this nice symmetric octahedral environment, to a distorted. So if you look at this V203, you see that the octahedron is slightly off. It's not perfectly symmetric. And then you go to this sort of layer type structure for V2 orthorhombic V205, and you see more of this 4p3d hybridization, and that's all because as you're increasing the oxidation state, right? Like say you have here, right? Your core level energy is also changing. Yeah. Oh, and if you really wanted to know, but you didn't ask, if you really wanted to know the emergence of these two pre-edge peaks, not just one. So here you see the shoulder, then you have essentially two, based on first derivative, you can resolve two shoulders, and then one peak here, and then one here, and then I guess one here. These two peaks has to do with the crystal field splitting. So in an octahedral environment, you have the T2G. Flashback to lecture 3, right? You have the T2G and the EG, so right? But then in the T2G orbital and crystal field, in the Untitled distortion, you have the 3D XY, XY, YZ, and XZ. The XY will actually split off from that degeneracy, and so you have now 2 in the T2G that shows up. And that's what also hybridizes with the 4P. So you have this split off because of the 3DXY orbital, breaking degeneracy in the T2G. Okay, all right, that's it. I'm done dancing, doing the crystal field dance. So I'll see you all next time.